Hello, everyone. Welcome to this week's seminar. Now, I notice we have a watch party here. You get to wave. That's a great idea. We're going to hear from two of our graduate students, Balsher Sidhu and Felipe Perez. I think I will just turn the mic over today to Kushank and Rudri, who will be introducing people.
Thanks, Terry.
Or introducing the session, sorry.
Welcome to the IRES Thursday seminar. As Terry said, we have two IRES students, Balsher Sidhu and Melgarejo, presenting today. Both this will be given 20 minutes to present, followed by a 10-minute question-answer session. Balsher will be going first, followed by Luis. And before we start, I would like to acknowledge that the UBC's Vancouver Point Grey campus is situated on the traditional, ancestral, unceded territory of the Musqueam people. I would also like to acknowledge that you're joining us today from many places near and far, and acknowledge that the traditional owners and caretakers of those lands. Now, I'll request Naveen to introduce Balsher. You, Naveen.
Thanks, Kushank. It's a real pleasure to introduce Balsher Sidhu. Let me first say that Balsher is joining us from India, where it's 1 a.m., so don't give him too much of a hard time. Balsher is co-supervised by me and Milind Kandlikar, who is also here with us. Milind has a class right afterwards, so I'll be doing the honors, but feel free to chip in. Balsher had a bachelor's degree from the Indian Institute of Technology in India, which some of you may know is one of the premier technological institutions in India, but maybe also the world. 1 million people apply and take an exam to get into the IITs, and something like a few thousand get in. Balsher was one of those lucky and talented few. I didn't get in when I wrote it a long time ago, so there you go. Then he did a master's degree in civil engineering from Toronto, and then he decided that he wanted to work on issues that he really cares about from the place he grew up in. So he completely switched gears and decided to come to a PhD with me and Milind in IRES. He's been doing some really amazing work digging into data and statistical models to estimate the impact of climate change on crop yields in India. I'm not going to say more about that because he'll be talking about it soon. Except that I think he's dug deeper into statistical models than most people I know. A lot of people just simply apply the models, and he's really dug deep into it. So nicely done. In terms of, so you'll hear about his work, but the other thing I wanted to say is that he's an amazing teacher and communicator as well, science communicator. He taught our climate change course in the Vancouver summer program for a couple of years. He's made a TED video on water. He did it without any of us knowing about it until it suddenly showed up on TED. He's written very insightful blogs about air pollution and farming in India. And most importantly, for those of you who follow him on Twitter, you will know that he's a very sharp political commentator, and he has a very sharp wit. And so always enjoy seeing his Twitter posts. With that, over to you, Balsher.
Wow, thank you so much, Naveen. I'm honestly overwhelmed, but yeah, that was, I think, the best introduction I've ever had. So thank you for that. So yeah, hoping everything works fine. I'll just share my screen right away. It says screen sharing has failed.
You probably are not host.
I am a host, but maybe I need to start my,
there you go.
Yeah, thank you. Okay, thank you everyone for joining us today. I'll jump right in. So today I'm going to talk about my current project where I'm examining the impact climate has on crop yields. Specifically for my talk today, I will discuss and compare two major statistical techniques that I'm using in my analysis. To give you a brief background, as we all know, agriculture is highly dependent on climate. both seasonal as well, such as the mean seasonal temperature or the total rainfall over the season, as well as within seasonal variability. So such as how many dry days there were, or how many precipitation days there were, or how many days of extreme temperature there were, like a heat wave. So these anomalies that may get overlooked if we only talk about the mean season are just equally important for crop yields, and that is a major focus of my work. And this seasonal variability has been a topic of extensive research recently. Apart from that, when we talk about statistical models to model crop yields as a function of climate, we have various statistical techniques available to us, starting from the simplest models such as linear regression, where the yield is modeled as a linear function of various climate variables, going all the way up to sophisticated machine learning algorithms where the computers, they extract the relationship between crop yields and climate without the researcher actually manually entering the model that they want to check. So I'll be discussing both of these in my talk today. To give you context to my study, my focus is on India, where I come from. Agriculture is highly dependent on monsoons in India. 2/3 of the net cultivated area is monsoon dependent, and it's estimated to produce 40% of the food grains nationally. And within India, while predicting crop yields as a function of temperature and precipitation has been going on for decades, research has been more or less limited to the seasonal average precipitation, and only recently have we started talking about within seasonal variability. For example, if there is a season with a short drought during the early growing stage, followed by a heavy rain event during harvest, if you consider the season on the average, the growing season on average, it will be considered as a season with normal rainfall. But even though those anomalies that I discussed earlier, they may have caused yield losses or even crop failures. So that is one of the primary motivations why we want to build statistical models that can incorporate these intra-seasonal climate variability parameters, and so that we can better understand the relationship between climate and agriculture. To begin with my seasonal model, I primarily have two variables. One of them is the mean seasonal temperature over the growing season of the crop that I'm modeling, and the other is the total seasonal precipitation. This data we acquired from the Indian Meteorological Department. It was provided to us at daily scale, and then we then we averaged it over the growing season to create these two variables. And so these are our independent variables, and the dependent variable was crop yields, which is available from the International Crop Research Institute for Semi-Arid Tropics. And this data is available from 1966 to 2011, so 46 years, and it's available for the whole of India, all the 300 plus districts of India, according to 1966 boundaries, that is. So we have data for the whole country for crop yields as well as climate, and all the analysis that I discussed at this point forward is for the whole country and using these two primary data sets. So jumping right into the simplest seasonal model with the mean seasonal variable. So I have only two variables, the mean seasonal temperature and the total seasonal precipitation. And this is the output that we get from running a linear regression. And if I want to, if we want to understand what these numbers mean, for every 1 degree Celsius rise in mean seasonal temperature, this model tells us that the crop yields will go down by 0.138 tons per hectare. And similar is the case with precipitation, and we can understand, or we can estimate the impact of precipitation changes depending on from this coefficient as well. However, as we discussed earlier, subseasonal climate variability is also important, and even more so because of climate change, which has shown that extreme wet and dry spells during the summer monsoons have actually been changing recently. There have been quite a few studies which have shown that while the mean seasonal rainfall may not have changed, the distribution has changed in the sense that rainfall patterns have become more erratic, which means that there are more extreme rain days, and then there are also more dry spells within the same season, even though the average rainfall may not have changed. So, and at the same time, we also know that the impact of temperature on crop yields is not linear, unlike the simple seasonal model that we discussed earlier, which is very common which is very commonly studied. For example, a 1 degree Celsius rise from 25 to 26 degrees Celsius would have a very different impact on crop yields compared to a 1 degree Celsius rise from 35 to 36. But a linear model, it says that the temperature change would have the same impact regardless of where you start from, if the simple seasonal model that we discussed earlier. So we need to build a better model to incorporate the within season variability. And today I will just focus most of my discussion on temperature for want of time. And I want to take some time to talk about degree days now. So degree days is a concept where you actually try to examine the impact temperature has, but in a nonlinear fashion. So what you do is you take a base temperature, which could be, let's say, 30 degrees Celsius, and then you see how high the temperature was above the base temperature and how long that temperature endured, or how long it was maintained. So for example, if you have 5 days at 36 degrees Celsius, then with a base temperature of 30 degrees, you have 5 multiplied by 6, you have 30 degree days. And depending on your base temperature, your definition of degree days would of course change. And the reason we use degree days is because our crop yield data is at annual scale. So we have only single value for every year, but our climate data is at daily scale. So we can't input all the daily temperature data into our model. So what we do is we try to make some compromises. So instead of using only the mean temperature, we break up our data into degree day bins. So we calculate the amount of time that the crop spent from 0 to 10 degrees Celsius, from 10 to 20 degree, 20 to 30, and so on and so forth. So that is one that is one way to do it, and that is the choice that we made. And that is shown in this schematic where I discuss my subseasonal model now. So on top of our seasonal variables, we add our degree days, so the amount of time and intensity that the crop spent in different degree day bins. And for precipitation, we just count the number of days when it rained over the season. So rain is defined as any day where the daily precipitation was greater than 0.1 mm. I'll show some example results from this analysis. So just to reiterate, we are still talking about linear regression, but we have degree days as extra variables in our linear regression now. So these, the plot on the right, it shows the coefficients for the 3 degree day bins that I discussed earlier, from 10 to 20, 20 to 30, and greater than 30. So essentially what this means is that if there are more days in the 10 to 20 degree bracket or in the greater than 30 degree bracket, crop yields go down. So there are losses. But if there are more days in the 20 to 30 degree bracket, then crop yields go up compared to what we are seeing right now. So if the climate were to get warmer, as it's happening with climate change, there would be more days in the greater than 30 degree bracket. So crop losses are expected to occur in the future as the climate warms up. So this is essentially a proxy for examining the linear impact of temperature on plant growth. And I'll just like the seasonal temperature, we'll discuss some numbers for the subseasonal. So for example, this point, it's approximately minus 0.0013. So what it means is that if there are 5 days at 35 degrees Celsius, 5 extra days at 35 degrees Celsius, So that's 5 multiplied by 5, 25 multiplied by this number. That is how much crop loss you would expect. So that's the way to interpret these coefficients. So now we've built a seasonal model with mean seasonal and precipitation precipitation. We have built a sub-seasonal model with some extra variables to account for degree days and rainfall. But and the next step was to see if there can be more flexible models using machine learning. And to just take a minute to discuss machine learning. So machine learning essentially in simple terms is when you throw data at the computer and the computer tries to discern relationship between the data. So what I do is I input crop yields and I input the climate data, and within certain constraints, depending on what kind of machine learning algorithm I'm using, the computer is able to discern some relationships which may or may not be linear. So there are fewer assumptions made about the relationship compared to a linear regression model. And the advantages, of course, are that you don't need to specify the model, and model interactions between different variables are included without having to write them manually. So a high temperature may have a different impact depending on how much rain occurred over that growing season. So those interactions, they can be taken care of in machine learning without you explicitly mentioning that. And the disadvantages, of course, are that machine learning algorithms, the output from these algorithms is not as interpretable. So if you remember the way we are interpreting the coefficients from the linear regression, that is not as easy to do in machine learning because there's a lot of calculation going on in the back end, and they are not always easily interpreted. Although there is some compromise that can be made in this as well, and that's a reason that we chose the algorithm that we are going to discuss next, which are called boosted regression trees. So they are a part of the machine learning ensemble, but they are also somewhat interpretable. So that was the reason we chose them. And regression trees are, simply put, they are a way to discern the pattern in data by dividing data into different parts. For example, so if we input temperature and precipitation in crop yields, and what the model does is it divides up data depending on what's the sweet spot when it comes to temperature. For example, it would say if temperature is less than T1, it goes to the left side. And if temperature is not less than T1, then it goes to the right side. And depending on so on and so forth, it goes down. And it tries to elicit the patterns depending on these bifurcations. And because we are not making any assumptions about the data distribution, BRTs can handle non-linearity pretty well. So they can continue to bifurcate data till they reach a point where further bifurcation does not have any more utility, and then they stop there. So compared to linear regression, BRTs can discern or identify non-linear relationships better. So just switching gears for a bit before we return to our beloved statistics in the next slide again. Irrigation plays a very critical role in agriculture, as everyone knows, and since crops receiving irrigation are better suited to withstand dry spells over the growing season. And India exhibits a large spatial variation in the availability of irrigation. This is shown in this figure where we have plotted the percent area under rice cultivation that receives irrigation across different states in India over time. So there is even spatial variation, and there is temporal variation. So there are some states which have historically had good irrigation for decades. There are some which still don't have good irrigation, and there are some which were primarily rain-fed, and then they rapidly shifted to the irrigated agriculture with Green Revolution. And because of these strong differences in the level of irrigation across the country, I have divided my data into rain-fed and irrigated before running BRTs on each. I'm not going to go into all the results that I got. I'm just showing one aspect as an example. So this is the additional impact that the time spent in the greater than 30-degree bin has. So this is the third bin that we discussed earlier. So at the top is irrigated agriculture, and we see that more or less the crop yields don't fall as much as the amount of time spent in the greater than 30-degree bin increases. But if we talk about rain-fed agriculture, which is shown in red at the bottom, we see that the more is the time spent in the greater than 30-degree bin, the crop yields go down. And if we compare this to the linear model, we see that the linear regression model fit a single value. So it says that X% of time spent in greater than 30-degree bin has Y impact on yield. But this BRT, because it's more flexible, it is able to account for the nonlinear relationships better. And this is one of the advantages of machine learning, as we discussed earlier. This plot shows my results in a different way, but it's again a reiteration of the fact that BRTs are able to account for nonlinearity better than linear regression. At the top, we have linear regression, and at the bottom, we have BRTs. On the x-axis is our observed yields. On the y-axis are the yields predicted by the model. So just to clarify over here, these are out-of-sample predictions over here. So what that means is my model was fit on 90% of the data, and it was tested on the other 10% that was held out. So there's no data leakage between training and testing. And then this was done for different 10% data sets in a recursive manner. So that is your classic 10-fold cross-validation. And the reason to do that is so you are not overfitting. So you're not showing the model the same data. You're not testing the model on the same data that you're training it on. So we did 10-fold cross-validation to examine how accurate the models are. And we see that the predictions of the BRTs follow the X equals Y line better than linear model. And now I'll just summarize my results that we've been discussing so far. And for that, I used RMSE, which is root mean squared error. So it's just a fancy term to summarize what I showed in the previous slide. So what you do is you take all your predicted values, you take your observed values, you take the difference between those two, you add them all together, you square them up and take the average value. So it's essentially the lower is your RMSE, the better is your model. And we see that compared to a no season model, where you only input, where you don't input climate, the linear seasonal model is able to account for around 2% more variation. So it reduces RMSE by 2%. But if you add some sub-seasonal variables, there is some improvement, and you're able to explain 3%, or your RMSE goes down by 3%. So the higher the bars in this plot, the better is your model. And if we look at BRTs, their improvement is massive compared to linear model, which is expected because they are able to they're able to account for a lot of non-linearity, and they're also able to account for the different interactions that can take place between the variables without us actually having to enter them manually. And one interesting result from this analysis that I would like to spend some time on is that the sub-seasonal model seems to be underperforming compared to a seasonal BRT. So because we are using 10-fold cross-validation, our hypothesis or our intuition is that maybe the model is overfitting when you throw in extra variables. For example, and this has big ramifications actually. So the sub-seasonal BRT, if it's not performing as well as the seasonal, it means just that maybe we don't need the sub-seasonal data, and the BRT is able to elicit all the information that it needs from the seasonal data itself. So I fortunately had seasonal data, sub-seasonal data, like daily data. So I was able to do all this analysis. But if one doesn't have daily data, if you only have seasonal values, then it seems like seasonal BRT could be a good way to just model crop yields as a function of climate. So this, of course, needs a lot of further analysis, because I've only done analysis for one crop, and that is only for India. So it could be the results could be very different for different crops in different parts of the world. And I would be very hesitant to say that my results can be translated or transferred to other crops as well without further looking into it. And to wrap up my discussion, the significance is that all these models, they help us understand the drivers of crop yields. So we know that climate change would affect crop yields, but it's always it's always good to be able to understand this relationship as well as possible. Furthermore, the Indian government has ambitious projects to expand irrigation throughout the country. So developing irrigation in currently rain-fed regions could benefit from this analysis, because one could identify hotspots where, or one could identify the low-hanging fruit actually, where expanding irrigation could have massive impacts. And then, of course, understanding crop sensitivity to climate change could help us adapt to climate change, both by improving our techniques or even crop switching. So that is those are the different directions that this analysis can be taken. And with that, I would like to wrap up my presentation, and I'm open for questions. Thank you.
Okay, thanks, Balsher. In virtual applause. We have a tradition in IRES. So the first couple of questions go to the students. Looks like Stephen from the watching party. Stephen, I can see you.
Thanks, Naveen.
Please go.
Thanks. That was a great, really interesting presentation. I was just curious about your decision to use BRT. So I used BRT in my master's and found it to be also really, really powerful. But I was also comparing it with some other like techniques like Maxent and random forest and things like that. And I found that it was not always the best model, and sometimes the other ones outperformed, and sometimes if you like ensembled the results of the models too, you ended up with like, you know, areas where they agreed and stuff like that. And I was mapping wetlands, so obviously it's different, but I was curious how you decided on BRT, and if you already tried some of those other models but didn't find them to be so successful and just aren't. Yeah, I was just curious about that. Oh,
okay. Thank you for the question. Yes, the one reason we chose BRTs was because they are sort of interpretable. Like they have these partial dependency plots that you can extract from them. And I remember I've tried neural nets in the past, and I don't know how well they performed with the BRTs. I haven't compared that, but they did have massive improvement compared to linear regression, and it is on my charts to compare neural nets and BRTs together. Yeah, but yeah, neural nets, as far as I know, they are less interpretable, so that was one reason we chose BRTs over neural nets. Yeah.
Sorry, I'm muted. I don't see any other hands up. Please raise your hands from the participants chat room. Hadi, I see your hand up physically. Go ahead. You're muted, Hadi. Hadi, you're muted.
Yeah. Hopefully I'm not muted anymore. Great talk. While you were talking, there was a big flurry of exchange between Naveen and I about your research. I'm wondering, really nice. And I know that you're aware that herbivory is a big challenge in this. Can you speculate on whether the subseasonal effects of poorer performance might be related to countervailing herbivory trends for your data that's driving the model? I'll listen to the answer.
Could you elaborate on that? So herbivory, by herbivory, I understand you mean pests are.
Yeah, so what I'm saying is that you have a process that is precipitation and temperature dependent for the growth of the plant. It's like a line integral. History really matters. It matters in which order you get this stuff and to the end, right? And then you've got got your nonlinear model explaining this in a very much better way than a linear model. Great, I really love that. But at the same time, the same factors influence the farmer behavior, farm additions, and herbivory. For example, if it's warm and the insects are growing fast, they're going to be very hungry. So if, for example, the kind of the optimal growth temperatures for the plants also correspond to a burst in herbivory, you're going to get countervailing processes of which you only see the residual in the yield. And so I'm wondering if the sub-seasonal poorer performance might be because you're conceiving this as one process, whereas in fact you have two countervailing processes, if not more.
I see what you mean by that, and I agree with you that there are a lot more processes going on. So I've heard instances of farmers they tweaking their techniques depending on what happened in the last season. So that sort of stuff, of course, is not covered by the model. So these are limited in that sense. So they can only look at the relations that you expect from the data that you input into it. So herbivory, in the example that you give, I'm sure it is conflating the results, but I don't know of a way I could examine that within the constraints of the analysis that I'm doing.
Okay, maybe we should talk about this afterwards.
Sure.
Thank you all. I think I'm going to refer to Kushank. I see a couple of more questions, but I think we are over time. Is that right, Kushank?
We have another 2 minutes, so I think we could take one more question.
Okay, so I have Gurcharan and Juan. I'll let you ask Balsher directly later.
So I will be quick. Thank you for the nice presentation. I really enjoyed it. Like Hadi mentioned, I think herbivory is one thing that might mask some of the results or what is happening in the real world. But I think more than that is there are many other factors like resistance to diseases and insect pests, and also some years we have epidemics of diseases, right? And some other years are disease-free years, so yield fluctuates. And I guess it is also hard for you to take into account every factor into your model, and I understand, but have you tried to work on the data pre-Green Revolution, post-Green Revolution? Because there was a huge difference in varieties bred after Green Revolution and before Green Revolution in yield. Because yield is your, say, dependent variable, right? And the other thing is, maybe I think from a breeder perspective, it will be good to divide your 5 decades because you are using 55 years of data. If you have, say, analysis from each decade, say first 10 years, then second 10 years, and to compare how climate is affecting yield in each decade, because I think temperatures are rising because of climate change, but also varieties are changing, right? I don't know, it's just a random thought, and I want to know what you think about it.
Yeah, so I didn't discuss this in my talk, but we have time as a variable in our models, and that time variable, it is assumed to account for these changes that occur because of better varieties over time, better technology, even better techniques, and in cases of disease outbreaks, it depends on if it's national or subnational. So there's a lot going on on the ground for sure, and that is if you look at my results, that is one reason that we are talking about 2 or 3% reduction in RMSE compared to a no climate model. So in the grander scheme of things, it's 2 to 3%. So the other 97% is unexplained by my model. And that is one of the limitations of statistical models.
Is that usual with your kind of research, like the models only explain, say, less than 5% of total variation?
It is pretty common, and I've verified that just to make sure I'm on. I wasn't making a mistake. Yeah, that this is pretty common. That climate, the variation explained by climate from these models, it's in this range. Yeah.
Okay, let's move on. Luis, I think.
Yeah, we request Jordi to introduce Luis, please.
Hello, everyone. For those who may not know me, I'm a faculty member at the School of Community and Regional Planning and an IRES associate. And I was away last year on research leave, so many of the second years may have not seen me around the seminars, but it's great to be back. And it's a pleasure to introduce Luis Melgarejo, a recent graduate. He defended his master's thesis just a few months ago in the summer. And Luis is from Colombia. And prior to coming to UBC, he was working in the Amazon forest. His research is at the intersection of food systems and biodiversity conservation. And he led, again, prior to coming to UBC, he led a forest protection program in the Colombian Amazon that promoted wild fruits by supporting farmers and startups shift away from ranching and illicit crop to agroforestry systems. So he'll be presenting his master's work on sustainable food systems and perceptions of sustainable foods here in Vancouver. So welcome, Luis.
Just a second. Can everyone see my screen? Just a second. Yep. Yes?
Yes.
Hello? Yes? Okay, good. So thank you, Jordi, and thank you all for being here. I would like to share with you the findings of my study entitled "Will the Trade of Amazon Foods Help Recover the Amazon Forest?" This is a study on the sustainable consumption of acai in Metro Vancouver. But first, I'd like to acknowledge that my family is very fortunate to live and study here at UBC in the unceded ancestral territory of the Musqueam people. Moreover, the inspiration to embark on this journey comes from a lifelong personal commitment to protect food biodiversity. My study also draws on the frequently unrecognized knowledge of the Hu, Puinaves, Ticunas, and other Amazon indigenous communities. I want to thank my research supervisor, Jordi, and my committee, as well as my colleagues, admin staff, and faculty at IRES for your continuing support. Now I need your help to share it wide and far as an eye-opener to mobilize sustainable consumers. I will follow in a much more succinct form the sequence and contents in my study as shown in this slide. Only when I finished my thesis, I realized that my study was not related that much to Amazon foods or even to deforestation. It all boiled down to you and me, us, and the changes that we as consumers, knowingly or unknowingly, self-driven or motivated by the food industry, are causing to biodiversity with our consumption preferences. It investigates alternative behaviors that could allow us to shift to a healthier, biodiverse, and more sustainable food system. This is because of approximately 300 plant foods traded globally, only 9 account for more than 60% of all the commercialized food output. The remaining 7,000 known plant foods are slowly and silently being driven to extinction, along with all the forms of life depending on these plants. I will expand on this research problem, or I should say opportunity. This is because Amazon Foods captured my attention while coordinating an environmental project in the Colombian Amazon. I realized then that payment for ecosystem services, RED+, and low impact agriculture we were supporting, such as eco-certified extensive palm oil in the upper right image, were not really bringing the social and environmental benefits that farmers and ecosystems needed. However, I found about a few entrepreneurships of Amazon traditional foods in agroforestry models, as shown in the upper right image, that did what no other project could: change relational values in proud Amazon ranchers and settlers to recover and protect the Amazon biodiversity while offering a stable income and even nutritional security. By the way, that's me working with Amazon farmers in the bottom image and some small, very interesting startups we work with on the right. Unfortunately, these initiatives have still little support compared to low impact agriculture and slash and burn practices keep rising. I needed to know if Canadian food regulations and other industrialized food regulations, food regulations from industrialized countries for the trade of eco-certified Amazon foods with and without a history of safe consumption in Canada, as well as consumer preferences, had a chance to contribute to recovering large deforested areas before agroindustry stepped in. There was a lot written on the supply side, but not on the consumption. So I chose the market of acai as my case study in BC, as this province hosts the second largest market in Canada for natural health products and health foods. Now, please bear in mind the scope and limitations of my study. This research is only applicable for land food systems within contested biodiverse landscapes, not on intermediate to highly intervened landscapes. Its focus is on acai as an Amazon traditional food, assuming sustainable harvesting or its production through endemic agroforestry models. Therefore, my emphasis on the trade of eco-certified acai and not just any acai. Bear in mind that acai, just like any other Amazon food, may also turn into a risk for biodiversity if it is extensively planted without any control. This is actually happening in Belém do Pará and other parts of Brazil, considering acai's market growth. But again, I am only considering eco-certified acai for the purpose of my study. My study explores the consumption preferences and attitudes towards eco-certified acai products, as well as other Amazon foods and their potential and limitations to solve the problems of biodiversity loss. I chose the consumption of acai products as my case study because it has an established market in North America with more than 15 years of being consumed. In Canada, it is sold as a superfood to boost the immune system, as it contains certain antioxidants with a higher capacity to reduce oxidative stress in cells compared to most fruits. Two species are predominantly commercialized, the Euterpe oleracea and the Precatoria, with the latter preferred as it carries fruits with smaller size, but many more stems, the one on the left. Sales of acai businesses within the health food industry have had steady annual growth rates of more than 8% annually, only in the United States. Now, considering this background and identified research problem, I came up with these three research questions. What are regulatory barriers and opportunities identified for the sustainable consumption of eco-certified Amazon fruits in Canada? How do demographic profiles of acai consumers relate to preferences towards social environmental concerns in the sourcing of their products? And finally, how do acai consumers in Metro Vancouver prioritize the combination of health, social, environmental attributes of their product when they make a purchase decision? So I needed both quantitative and qualitative methods, but before, I'd like to share a bit on my lit review. In order to respond to these questions following a scientific method, I did a lit review and developed a conceptual and analytical framework centered on the sustainable consumption of Amazon fruits in biodiverse landscapes. Sustainable consumption is an evolving concept. I worked on the following definitions, starting from Max Neef's relation of human well-being and resource use, moving towards Lorik's effective resource use from a multidimensional development approach. And finally, for food system producing contested biodiverse landscapes, I drew from Campbell and Lorik's acknowledgement of planetary boundaries, as sustainable consumption comprises the ethical responsibility that attains to all of us to recover and protect depleted natural landscapes, following a biodiversity-centered approach that rather than a low-impact or carbon-centered approach. Now, the use of social media by influential consumers of more socially and ecologically ambitious land food systems is shown in the picture here. And we know that Instagram, Twitter, and Facebook have had a crucial impact on the market value of acai and other Amazon health foods and products. Unfortunately, not that much on the social and environment, on sharing the social environmental information behind these products. I then designed this analytical framework based on the theories of sustainable consumption and its link to food value chains. Different internal and external variables of a value chain influence sustainable consumption behaviors individually and collectively, and how consumers shift between these levels, ranging from the conventional mass trade, GMOs and the green revolution to end world's hunger to today's low impact fair trade and organic produce, further supported by the SDG 12 on sustainable consumption and production. However, we are starting to see a more ambitious approach to sustainable consumption that goes in line with the critical situation of biodiversity loss and climate change. My study goes in line with recent research that suggests that such a transition is happening as of now, and that younger, informed, influential, and hyper-connected sustainable consumers are interested in contacting directly and empowering farmers and ensuring their purchase decisions contribute to something greater than just reducing plastic packaging, food waste, and carbon emissions. To answer the first research question, I did a comparative regulatory analysis, taking the US and the European Union as contrasting food regulations to interpret those from Canada. I have also reviewed eco-certifications from assay products using biodiversity and natural landscape recovery lenses I developed. As for my quantitative analysis, to answer research question 2 and 3, in order to test hypotheses on intergenerational changes of sustainable consumption preferences of assay consumers, I have collected an in-person and online 5-point Likert survey during the fall of last year and a product attribute ranking with a sample size of 160 assay consumers living in Metro Vancouver. I used order logistic regression and Spearman's row rank correlations to test hypotheses on the relation of demographics and Likert responses. You're aware that this is a study with non-parametric and categorical data. Now, I'd like to explain a bit on my variables for the quantitative analysis. So for my dependent variables, I had Likert statements capturing consumer preferences on the knowledge of the sourcing of acai, the willingness to pay a conservation premium, which is hypothetical, and the reliability on eco-certifications. For my independent variables, I use basic demographics such as age, income, education, and ethnicity. For the third research question, I use a ranking attribute weighting exercise and purchase decisions of assay products, considering 5 attributes. First, the price. Second, appearance and quality. Third, a hypothetical attribute, which is a satellite monitor protection and recovering of Amazon forests attached to a product. 4, paying a fair price to farmers, and 5, health and nutritional benefits. Now, let's move on to the findings and discussion. I'll start with the qualitative analysis. This diagram summarizes the results of the comparative regulatory analysis by contrasting Canadian, US, and EU food regulations for fruits with and without history of safe consumption in these regions. Considering the limited time, I will only briefly explain the first 2 comparative factors, the upper part, as I want to bring your attention to these findings. On the level of preciseness and easiness for an importer to bring Amazon foods without history of safe consumption, when framed as traditional foods, as it has been implemented in the EU regulations, there is more clarity compared to the GRAS, or generally recognized as safe approach from the United States, or compared to putting these foods in the same bucket in the general group of novel foods, such as new GMO techniques that exist in Canadian regulations. However, Canada does consider the history of safe consumption in third countries as an important factor to grant approval. As for the social and environmental traceability of Amazon foods and food ingredients, Canada and the US expects importers and certification agencies to verify compliance, whereas in the EU, pressure from environmental NGOs is demanding more control to government agencies, especially for palm oil. But in general, traceability remains a major challenge. One of my key findings, after reviewing USDA and Canada Organics, Fair Trade, and Rainforest Alliance certification, using the Amazon's biodiversity and landscape recovery lenses proposed in my thesis, I must say that none of these specific standards made major contributions to the recovery of biodiversity and traditional foods in this region. They only provided best agroecological practices and recommendations, which are very good for highly intervened landscapes, but not for contested biodiverse landscapes. Now, stepping into the quantitative results, I should point out that most of my respondents turn out to be females in the age range of 19 to 29, and substantially fewer than those older than 50. I was expecting this considering the product. This did not compromise the statistical analysis. Nevertheless, we had a rather good and diversified representation in terms of income and ethnic background. As you can see in the density plot to the left for the Spearman's rank correlation, there was no significance between the willingness to buy more Amazon foods clinically proven to reduce the risk of a disease and the consumer's age and income. That means also youngers are more concerned also about their health and the food they're consuming. And however, About the 75th percentile, most consumers agreed and strongly agreed that health and nutritional claims are influential in a purchase decision. As for eco-certifications, one of the findings that struck me most, older consumers were more likely to trust organic and fair trade in the protection of the environment and securing a fair pay for Amazon farmers. Contrary-wise, there was a general distrust of younger consumers in these certifications and their capacity to protect the environment and rural livelihoods. In this web diagram, you can see in the countries in Likert items 4, which says organic certification, the first thing I look for in my assay products, and 11, which says, even with certification, I'm still concerned if my assay is deforestation free, how this interesting intergenerational difference is portrayed. As for consumers' preference in supporting a conservation premium or extra value in their assay products to recover and protect the Amazon forests, there was no significance with its relation to age and income. Yet 53% of all respondents and 86% of all 19 to 39 age respondents agreed and strongly agreed to pay a conservation premium to protect, if it really protects the Amazon regardless of income. Lastly, as consumers were asked about the relationship between assay products and the Amazon forest, most of them did not know about this or were not aware of this. In terms of the attribute ranking, taste, appearance, and health benefits of Amazon products still prevail with less variance, but a hypothetical mechanism to protect Amazon forest ranked slightly higher than price and fair trade. Innovative, reliable, and ambitious market-based conservation mechanisms are not only appreciated, but necessary in food biodiversity market niches, as according to this finding. This also means that given the social environmental philanthropy from certain concerned assay consumers, they are not willing to sacrifice taste, appearance, and health benefits in their products for an environmental or social cause. Food safety, appealing products, reliable scientific and clinically proven health and nutritional claims, and a competitive price still prevail. I will now like to wrap up with this slide listing the most important conclusions. Now, going back to my first and second research question, my study shows that opportunities outweigh the limitation in both Canadian regulations and the observed sustainable consumption preferences in the industries of natural foods and natural health products for Amazon traditional foods. In our case, acai, but this could be also applicable to other promissory Amazon foods, such as camu camu, kupuasu, and other nuts that are being promoted in many of these RED Plus projects or in many initiatives to recover biodiversity. Nevertheless, being a multicultural country, Canadian consumers and businesses could benefit more from the EU traditional foods regulatory approach. For the last research question, for the third research question, my research points out that crucial information on the social and environmental benefits of Amazon products in protecting forests and species diversity vanishes somewhere from the supplier to the retailer and the final consumer. We see a lot of advertising of this from the side of the exporters and importers, but retailers usually do not share that information. Imbalances in food regulations and trade, as well as marketing information gaps in the consumption side, could be indirectly facilitating the loss of food biodiversity by making it substantially more expensive and difficult for Amazon foods without history of safe consumption to be sold in Canadian supermarkets compared to eco-certified palm oil, or soy being produced in many of these contested biodiverse landscapes. Several questions arise. Are certified acai retailers losing product and brand value by not sharing this information? How can we develop trustable market-based mechanisms, regulations, and technical assistance that works with all the stakeholders of the value chain, not just the supplier, not just suppliers, and support transitions to biodiverse foods, land, and landscapes? Some tools I can think of, QR, barcode reading info and apps, GIS supported conservation agreements to empower influential consumers, suppliers, and retailers, and helping them connect with existing conservation and landscape recovery initiatives. Finally, we need to urgently invest in biodiversity food literacy. way more than First Nations and Indigenous people used to do, you know, to teach their young generations and how to protect food biodiversity. They did not have to deal with powerful food corporations back then. So our foods go beyond feeding us and our health concerns. I believe leveraging our consumers' ambitious relational values could lead to positive changes in natural landscapes. It is up to us to support biodiversity-centered food systems for the subsistence of mankind and all other forms of life on this planet. Now, I've been thinking about research outreach strategies. I'm working on a sustainable food consumer biodiversity pledge with 10-point levers that I can share with those who are interested in. I'm working also on a policy brief with former contacts in Canada, Norway, Germany, and UK, countries that are supporting REDD+ initiatives and the fight against deforestation in the Amazon. And of course, some quick fact sheets with for acai retailers and suppliers to to also show what some of these initiatives, especially those who are eco-certified, are bringing also not just to farmers but also to nature. A very small quote I like to share with you that I came up with this. If you don't decide what you want for food and how you want it brought to your table, others will decide for you based on their own interests. So with this, I'd like to finish and set then space for the questions.
Thanks, Louis.
Thanks, Louis. This is great. And you were right on time. Amazing. Rudri and I will help you moderate the questions. So if you're open to questions, please feel free to raise your hand, virtual hands, or drop a question in the chat box. I don't see any hands. Any questions?
Feel free to write in the chat box as well.
Okay, Susanna has one question. Susanna,
Sure, I'll venture a question. Nice work, Louise. Nice to see you.
Thank you.
Thank you for that presentation. As you know, I work on organic certification, so I'm curious about, I guess you mentioned some other possibilities for apps and other maybe technological opportunities to bridge that disconnection between the producer and conditions of production and consumer. But do you see potential for a certification, whether it's building on organic certification or something else, to really accomplish sort of what you envision as the ideal for acai products?
Yeah, that's a very good question. And I think this does not apply only to Amazon foods, to protect Amazon foods, but also many other of those 7,000 other plant foods. I believe after doing my research, I believe that there should be different certifications for depending on the level of intervention on a landscape and on natural resources, and also on the ecological value of where these products come from. So organic, it's very important, especially for highly intervened landscapes, to recover and to avoid, especially the use of harmful chemicals. But they do not really, I mean, for low intervened and high value like natural landscapes, you need to go beyond organic. And for that, I created, I don't know if I should share it quickly, but I created these, this is a very simple, so I don't know if I could just quickly show you this. Oh no, but I shared this. This one, these are the lenses. It looks like lenses, but oh, here are my lenses. So I can share this with you later, but I think that there should be some biodiversity lenses and landscape recovery lenses, so that an ideal certification should look into how a food is supporting trophic levels, prioritize endemic over introduced species, recovering ergonomic properties, how that product recovers or what impact it has, but also in the landscape, ecosystems and local diets are protected and supported. Satellite and forest conservation agreements, this is something we need to work a lot, especially between consumers and producers, and the recovery of forest and landscape matrices. So this is, yeah, this is something that I think should be done, or we should be heading towards that path.
Any more questions for Lewis?
I just want to say great job, Luis. Maybe do you want to talk about your policy memo that you're developing and where that might be going?
Yeah, very briefly, I'm trying to talk to those who are investing in VET Plus. They invest large amounts, and FCPF, which Canada is putting a lot of taxpayers' money to recover, to fight against deforestation in the Amazon. But many of those initiatives are supporting the low impact and carbon-oriented, carbon-centered solutions, and not that much on the biodiversity-centered solutions. So I'm trying to show, or of course, very respectfully, and tell them that it's all the good things that came from all those investments from Canada, UK, Norway, in Brazil, in Colombia, and Ecuador. We have now a more robust carbon monitoring system and also satellite monitor systems to address deforestation problems. But we definitely need to go beyond the carbon-centered and the low impact approach if we want to have a a higher impact in terms of biodiversity loss, like reducing biodiversity loss and supporting also nutrition and diets, both in producers and in consumers. It's really, I'm impressed. Like, we have so much biodiversity that perhaps something for a PhD would be, I know that how that economy plays a huge role there. If you have less products competing with your own, with specific foods, then, but in a globalized market, then you need to develop some other mechanisms to make sure that those 300 fruits will not, wipe out with population growth the other 7,000 fruits. This is something that I still keep thinking about, and what would be the next steps. I think we'll have to do more research on identifying how did we get into this mess, and how can we solve this problem.
Do we have time for one last question for Luis? If there are no more questions, Terry, would you like to close?
Okay, thank you. Thank you all.
Thank you, Luis and Balsher, and also Jordi and Naveen for your great introductions to give us a sense of what they're working on. And thank you, everybody, for being here in the first place, from your distant points and near. Thanks again. I'll see you next week. Same time, same place.
Thank you.
Thank you.